Pierre du Baret is the General Manager of MGP Mini Green Power. So I guess this is what you will present right now. Pierre will talk about biomass-based energy. Okay, so Pierre has a long industry career, working in trucks industry for 10 years, in Africa and in Finland. Afterwards, he joined the Pechiney Aluminium Group, and where he became the Deputy General Manager. Okay, now Pierre is working for MGP, and Pierre is graduated from the leading French business school, HEC. And he has also a degree in mechanical engineering from the university and a BA in law. Okay, Pierre, thank you very much for this presentation. You have 20 minutes for presentation and 10 minutes for discussion.
Okay, well, thank you, Patrick, and good afternoon to everyone. My speech, although it is on biomass, is actually somehow connected to the previous speech on microgrids, because the topic which I would like to develop before you is energy independence using one particular technology, which is biomass energy. Biomass has one key advantage over some other renewable energy. It's that it can work day and night. It's not only depending on wind or sun. It shares that with geothermal energy as well, but geothermal is not so well distributed as biomass. Of course, the best use that you can make with biomass is to use the heat, but we all can also co-generate, and that's where we will join the subject of microgrids. One of the challenges with biomass is the rising cost as when biomass energy grows, there often are tensions on the supply of biomass fuel, and this is really a hurdle to compete with traditional fossil fuels. Everyone likes biomass energy, but nobody wants to pay more for heating or cooling or electricity from biomass than from their current fuel. So this is a real challenge that we face wherever biomass has grown significant. And what we have tried to do at Mini-Green, we are a new company, we're 5 years old, we're a startup company, you could say, and we are trying to go for waste biomass from agriculture or forestry, for products which are not being used currently as biomass fuel, so that we don't compete with other usage and that we maintain or benefit from a low cost of fuel. The technology we are implementing for that is halfway between gasification and traditional biomass boilers, you could say. So we have invented a name. We're speaking of gasiotherm or gasiogens, depending whether we just make heat or co-generate. We don't know if it will be as successful as some other names which become common names but we hope. What I'm going to walk through is basically to tell you how we try to build a business case with this technology. The whole point of this is to provide competitive energy with renewable means. So we have not started from scratch. We actually are using some traditional technology items or combustion items, but we have used data processing and controls to make them more flexible. One of the limitations of the current biomass system is that they require calibrated fuels. So you can use wood chips, but they have to have this moisture level, or you can use other byproducts, but they have to be always the same, which is a drawback because then the price tends to get higher. We have tried to bring flexibility into the biomass energy, and for instance, we can use what we called green waste, that is to say freshly cut wood or trimmings, small pieces of wood. I mean, that's not so relevant here, but in Europe, for instance, if you do some gardening, you can't burn the branches in your garden. You have to take that to a municipal depot, and this creates huge amounts of biomass, which municipalities don't know what to do with. It's too wet to being used in conventional boilers, and therefore it usually goes to dump sites or to incineration, and it costs a lot to the municipality. We are able to use this material after a simple shredding and sorting to separate leaves, for instance. In leaves, there is mostly water, there is no calorific value, so of course it's of little interest. So that's a very wet product. But we can also use much drier products, which come from household waste, like old furniture. In the old days, you had family furniture going from generation to generation that you inherited. Nowadays, few people inherit furniture or keep old parents' furniture, but you buy new furniture from wherever, and after moving 2 or 3 times, this furniture will end in dump sites. So we can use this used wood, which is, or even if it is contaminated with like IKEA type of furniture, and this is pretty dry material. Other people can use it as well, but our difference is that we can go from one to the other. We can go from wet to dry instantly through just a simple menu selection on the controls of our machines. And that's just an example, but I could add to that agricultural residues such as rice husk or rice straw or cocoa shells or whatever. Whenever there is a calorific value of at least 1.8 kilowatt or megawatt hour per ton, we are able to use this type of fuel in our machines. The key to this technology is that we have separated the combustion in phases. This is why I'm speaking of staged combustion. We basically have a stage where we gasify, we burn a small fraction of the biomass to gasify, to heat up and gasify the rest. And then in a separate place, we burn this gas immediately. We are not trying to use this gas, this syngas, into an engine, an internal combustion engine, which is a traditional way of gasifiers, because this gas is quite often dirty. It comes from waste, so it's hard to have a good quality gas. The wood has not been dried, or it is varying quality in moisture and in nature. So we get a gas which can have a lot of tar or all kinds of impurities, and we don't try to purify this gas, we just burn it afterwards with long stays, long time at high temperature, so we're able to basically burn any harmful component. We have the time at high temperature that you could find in an incinerator, for instance. So this ensures that we have a fairly clean gas. It is exhaust gas, but it is relatively clean, and it can be used in a relatively ordinary boiler. I'm just going to move to this process chart. I don't know if this is, can we show something with that? No. The heart of the process is what you see on the top left, where you see a cylinder with 2 air injections. That's where the gasification takes place. And then you have a tube which is the place where combustion takes place. And the big difference, it may not look so different to conventional boilers, but the big difference is that by having two separate areas where we manage the process, we're able to regulate very, very accurately the pressure, the amount of oxygen, and we can do that independently or with very little interaction between one place and another, and that helps us to have a very good control of the combustion and to accommodate varying types of fuels. And after that, we have also a hot temperature cyclone, which contributes to have these long times at high temperature, which allows us to crack all the tar components we can have in the gas, in the syngas. And after that, we have a pretty clean combustion gas going into a boiler, or actually I should say a heat exchanger, because we have removed about 95% of the ash in between the gasifier itself and the cyclone. Once we have done that, we fall back into conventional technology. So you can add to this any type of steam generation device or boiler for hot water, and you can combine that with whatever power generation system. Here what is shown is a steam turbine in this particular case, we have around 1 megawatt electrical, and downstream from the steam turbine, we generate hot water. This one is intended for a greenhouse, and therefore we co-generate. To give you a flavor of what it means in terms of isolated system, if we don't sell the heat, if the heat has no value, here we are able to generate at electrical power at a price in the region of 140 euros per megawatt hour, which is around, or per kilowatt hour, let's say, 4.7 baht per kilowatt hour, which is pretty expensive if you compare it to main grid prices, but which is quite competitive if you compare it to diesel-generated power. So this makes this solution, even if you don't sell the heat, this makes it competitive for off-grid areas where the competing generation devices are diesel-powered. And of course, if you sell heat, then the economics are much better, and you can get power prices which goes down drastically. Because in this particular example, you have an electrical efficiency over heat generated, which is around 20%. So this means that 80% of the heat that has been generated is basically dissipated. But if you're able to use this heat to co-generate by providing steam or hot water or cold water to any user, then of course this is improving drastically the economics, and it enables you to lower the cost of power. So one of the good subjects to implement such systems are hospitals, any user of both electricity and heat, or industries, food processing industries, or similar type of industries. In Europe, of course, we use it for greenhouses because in many places greenhouses are requiring heat 10 months out of 12, but that's not the case here, so here it will be for other applications. Yeah, so that I was ahead of my slide for applications. The best in this technology, the cost per megawatt hour is actually mostly made of the depreciation cost of the asset and operation cost, which are mostly fixed costs. So what makes this energy competitive is the ability to provide energy 8,000 hours per year, day and night. That's where you will divide the fixed cost by the highest number of kilowatt hours or megawatt hours, and where you will have competitive applications. So basically this brings us to the aim of a closed loop energy approach. The idea is that you build the plant. These are small plants. They are producing between 40 kilowatt electrical up to 1 megawatt electrical, or 500 kilowatt thermal to 6 megawatt thermal. So you build that where you need power. And then you get around to find the type of fuels, because we are so flexible in fuel. You usually can find around the plant the fuel you need to fire it. I've been mentioning biomass, but we are actually also developing a version of this plant for so-called RDF, refuse-derived fuels, and that's coming very soon. And sometime later we'll go for solid municipal waste with less preparation. So the idea is that in places you don't have biomass available from forestry or from agriculture, but you do have waste, and you can implement this type of solution also to provide energy in a closed loop, which is what we fight for. Just to give you a flavor of the economics, this one is so here this is focused on heat. This case is more for a greenhouse. A fairly large greenhouse, because it's 4 hectares or 40,000 square meter. I made a choice to depreciate the asset over 6 years, which is a fairly short time, considering that these types of machines are designed for at least 20 years of operation. But it's just to give an example. And I've put a figure of operating and maintenance, which is in France. It would probably be different over here. And then the fuel cost. In this particular case, this is green trimmings. At the price I have to pay for it in France, which is, by the way, a quarter of what would cost conventional wood chips. And with that, I'm able to deliver heat to a greenhouse at about 30 euro per megawatt hour. You have the Thai baht equivalent just aside, and that's basically very competitive even against natural gas in Europe, because the natural gas in Europe without operation and boiler cost is already costing 20 euros per megawatt hour. So just the fuel, just the natural gas which comes from the pipe is already costing 20 euros per megawatt hour. So when you add to that the cost of depreciating the boiler and maintenance and operation, you're easily in those level of prices. So the message here is that if you are able to sell the heat, you have a good business case which is already competitive against fossil fuels. Of course, natural gas in Europe is influenced by the fact that there are some taxes, so may depend, may vary according to country, but that's comparison was made for France. We also do what we do with emissions in mind. That can be an issue for biomass boilers, and this type of combustion we are doing brings us a benefit over the emission of nitrogen dioxide. You have here the comparison between conventional boilers, you see the limits, the EU limits. The green dotted lines is the EU limit for nitrogen dioxide, and the green fluctuating line is what the emission we have on our machines. And we are roughly halfway through under the limit, where conventional boilers are quite close to the limit. And what we are doing is to use this leeway to go for dirtier fuels, which often are richer in nitrogen. So we have leeway to accommodate products or fuels with higher nitrogen content. But of course, if the nitrogen content is very high, we shall have to do as others do, that is to say, to use urea injections or mitigating devices to reduce the nitrogen content, which is one of the pollutants which are under scrutiny, at least in EU. Of course, we also work on dust, which is an issue. But that everybody can do that with proper filters. And then if we go for dirtier fuels with glue or paint or whatever, then we will have to do further fume cleaning with active coal or bicarb or whatever devices which you can find on the market. I think that's about what I wanted to say. I have more slides about who we are, but maybe I shall keep that if there are questions. Thank you.